In Lecture 5B, we will learn to construct and interpret box plots and how to identify outliers in a distribution. Spatz does such a nice job explaining box plots, and I think I'm just going to go ahead and quote page 77 almost in its entirety so that I can add the annotations to what he is explaining in the text about interpreting box plots. To start off with, box plots show you lots of different things. The first thing they show you are two measures of central tendency. The vertical line inside the box is at the median, and the dot is the mean. In figure 5.2, you can estimate the median as 25 and the mean as slightly less. It is actually 24. Variability. Both the box and the whiskers in figure 5.2 tell you about the variability. The box covers the interquartile range, which you studied in Chapter 4. The left end of the box is the 25th percentile score, and the right end is the 75th percentile score. You can estimate these scores from the horizontal axis. The horizontal width of the box is the interquartile range. The whiskers extend to the extreme scores in the distribution. Thus, the whiskers give you a picture of the overall range. Again, reading from the scale in figure 5.2, you can see that the highest score is 35 and the lowest is 5. Skew. Finally, both the relationship of the mean to the median and any difference in the lengths of the whiskers help you to determine the skew of the distribution. You already know that, in general, when the mean is less than the median, the skew is negative. And when the mean is greater than the median, the skew is positive. The relationship of the mean to the median is readily apparent in a box plot. Skew is also usually indicated by the whiskers of different length. The longer whisker tells you the direction of the skew. Thus, if the longer whisker is over the lower scores, the skew is negative. If the longer whisker is over the higher scores, the skew is positive. Given these two rules of thumb to determine skew, you can conclude that the distribution of the SWLS scores in figure 5.2 is negatively skewed. Let's go through the questions that Spatz asks about figure 5.3 in your text, and just make sure that we understand how we can look at multiple box plots at a time to come to some interpretations. Alright, the first question he asks is, which distribution has the greatest positive skew? Alright, just to review, a positive skew means that the tail is on the right. Okay, and that also means that the mean is greater than the median. So the mean would be on the right-hand side. So I'm looking for any of the distributions where the dot is to the right of the line, the dot being the mean and the line being the median. So that means I can look at distributions A and D by themselves for first question, because the other ones are negatively skewed. Alright, the second thing that we look at is the difference between those. The greater the distance the mean and the median are, the greater the skew. So based off of that criteria, I'm guessing that D is going to be the greatest skew of the three. I just want to verify one last thing, and that's the whiskers. In a skewed distribution, the whiskers will be longer on the side of the skew. And in D, it is indeed longer on the right-hand side, which would be the positive side, than the left-hand side. And then in distribution A, they really look about the same. So all of those things together add up to a conclusion that the answer to question number 1 is, in fact, D. D has the greatest positive skew. Okay, let's take a look at question 2. Which distribution is the most compact? In terms of being compact, we want to look at the size of the box. A larger box is going to have more variability than a smaller box because the box rate number represents the interquartile range. Also, you have to look at the whiskers out to either side of it because they stretch from the data minimum to the data maximum. So looking at all four distributions here, the obvious choice for most compact is choice C. It is the one that has the smallest box and the smallest whiskers together. So correct answer for question 2 is C. Okay. Question 3. Which distribution has a mean closest to 40? Now remember, the mean is the dot. So I'm going to find 40 on the horizontal axis, and I'm going to draw a line up, and the one that has the dot closest to 40 is again distribution D. So correct answer to question 3, distribution D has a mean closest to 40. Okay, and next, which distribution is the most symmetrical? Now remember, symmetrical distributions have a mean that is essentially the same thing as the median, and we wouldn't be looking for a whole lot of variance in the lengths of the whiskers on either side. So the one that's closest, I think it's going to be A, because that one balances equal whisker lengths with a similar mean and median. They're not exactly the same, but they sure are close. The next best choice would probably be C, and I see that the whisker lengths are really quite different on C compared to A. So for most symmetrical, I'm going to choose A. And question 5. Which distribution has a median? Remember, that's represented by the vertical line closest to 50. So here's 50 on the horizontal axis. Draw that one up, and it's immediately apparent that distribution B is the correct answer because its vertical line is almost smack dab, if not on, the score of 50. Question 6. Which is most negatively skewed? Well, we discussed positive skew in question number 1. Remember, negative skews have tails to the left, and that means that my mean, which is always closest to the tail, is going to be smaller than my median, and that means my dot will be to the left of the line. So I can eliminate choices A and D, and I need to look at B and C. And now I want to do two things. I want to look for the distance between the dot and the line. The greater that distance, the more the skew. And I want to verify that the whisker length is also longer on that same side. In this case, we're looking pretty obviously at distribution B because I have a larger difference between the dot and the line, and I have a clearly longer whisker on the left that's more dramatic than, say, the longer whisker of C on the left. So correct answer to number 6 is distribution B. And last but not least, which distribution has the largest range? Well, the range is most easily represented by looking at the whiskers. Remember, the far left whisker ends at the minimum, and the far right whisker ends at the maximum, making distribution A the largest ranged distribution. Again, quoting Spatz, this time page 75, outliers are scores in a distribution that are unusually small or unusually large. An outlier has a disproportionate influence compared to any of the other scores on the mean, standard deviation, and other statistical measures. They can certainly affect the outcome of a statistical analysis, and they appear to be fairly common. Although there is no general agreement on how to identify outliers, Hogan and Evelenko found in 2006 that the most common definition in statistics textbooks seems to be using the 25th percentile and the 75th percentile and either subtracting or adding 1.5 times the interquartile range. Let's use this common definition for finding outliers in a set of data to identify the boundaries below and above which a score would be considered an outlier. For this example, the 25th percentile is going to be at a value of 12. And the 75th percentile is going to be at a value of 18. And these were just provided. That means my interquartile range, my IQR, is the difference between those, or in this case, 6. Applying this IQR of 6 to my formula, my 25th percentile was 12, and I want to subtract 1.5 times the IQR, which is 1.5 times 6, to find that value. 1.5 times 6 is 9, and 12 minus 9 is 3. For the upper outlier, I'm going to do the same process, except for this time I'm going to use the 75th percentile, which was 18, and add 1.5 times the IQR. So it's still 9 as the 1.5 times the IQR. 18 plus 9 is 27. So what I'm going to do is to graphically depict this, I'm going to extend my number line here down to where 3 would be, and up to where 27 would be. And now I know that if any observations or scores fall outside, so say if it were 2 or 30, that these values could be safely classified as outliers. For our last example, let's evaluate certain scores given a 25th and 75th percentile to determine whether they are outliers or not. So I'm going to start off with this problem by kind of setting up that number line that we've been using, just to understand that these scores are all continuous. And I'm going to center 10 and 20 as the 25th percentile and the 75th percentile. And I can see that from this, my IQR is 20 minus 10, or 10, which means that this ratio, 1.5 times the IQR, is going to be 15. So my boundaries for what I will consider to be outliers are going to be 15, and it's not really drawn a scale here, sorry about that. Ideally, these distances should be 1.5 times the length of my IQR. But it's going to be 15 higher than the maximum 75th, so that's going to be at 35. And 15 lower than the 25th percentile, which was 10, so 15 lower than that is negative 5. Now let's evaluate the scores. Score A is 6. Well, 6 is going to be somewhere around here. And it's within this boundary set by these limits from Hogan and Evelenko. And so I would call a score of 6 not an outlier. A score of 37, however, is going to be outside the limits. So yes, 37 would be classified as an outlier. And also a score of negative 9 is going to be lower than negative 5, making that an outlier as well.